recorder. The recorder is on. Move this out of the way. All right. All right. So on Monday, we talked about how there are choose three many ways to have exactly three heads and two tails in five coin tosses. So that's what we talked about on Monday. And what we'll talk about today is so if you are to actually flip a coin exactly five times, what are the chances that you end up with three heads? Okay, no matter where the three heads are. Okay, so you can have head, 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 tail, tail. You can have head, tail, head, tail, head, tail, tail, head, 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 and so on. And then also on Wednesday, we also talked about how um, there are exactly 10 of those cases. We actually enumerated, we listed all 10 cases. Also, on Monday, we talked about how we can kind of look at this problem as a combination problem. Because, in other words, we look at the positioning of the coin tosses, one, two, three, four, five, first, second, and all the way up to fifth, and then we are really just asking, um, how can we choose three out of the five positions to be the heads? So imagine that you have a bag with one, two, three, four, five as slips of paper in the bag. You have to pick three of those five pieces of paper. The ordering is not important because you can pick out a five first, pick out a four next, pick out a one next. So that means the first position, the third position, and I think the fourth position will be heads of the five coin tosses. So that's what we talked about on Monday, and I hope you guys had a chance to review that material and get that stuff already cleared before we continue on the topic of coin tosses. Yes. You mean when is the final exam? Oh, you mean exam to the results? Yeah, not yet. uh, I do have all the keys already done, but I have to manually go back and actually grade every single one. So no chat GPT or any type of AI used, when in the process of grading. It's very organic. Hmm. So anyway, getting back to this. So the chances would be the total number of ways you can end up with three heads and two tails divided by the total number of ways of outcomes of five coin tosses. So based on the discussion on Monday, the previous class, how many ways can we end up how many outcomes, okay, in terms of experiment, what is the total number of possible outcomes of tossing a coin exactly five times? Do you guys remember that tree that I drew and I was running out of space? It's not combination, the total number of possible outcomes. So it's neither a combination nor a permutation because coin tosses intrinsically is with replacement. 32. That is correct. So that means we are really looking at 10 divided by 32. That is the chances of having three heads out of five coin tosses, assuming the coin itself is not loaded. So that means you have an even chance of landing on the head versus landing on the tail. Is that okay? All right. So assuming, because I cannot read minds, assuming that is okay, so that means we are basically done all the way up to here, okay? So the event set in this case would be the subset of omega, where there are three heads and two tails, and then omega itself is basically the tree of 32 leaf nodes that we talked about on Monday. So do we have any questions about this stuff at this point? No. Okay. Okay. Assuming there are no questions. So the next thing that we need to deal with, okay, let me just kind of increase the font size a little bit. I think that makes it a little bit easier to read. So assuming that the coin is not even, which means it is loaded, What do we do in that case? In other words, if we know that the chances of landing on a head is P and the chances of landing on a tail is Q, and Q has to be 1 minus P, what do we do in that case? So the first thing is a graphical representation, but this time I'm going to shorten the whole thing to only 3 coin tosses instead of 5 because, as we already have seen, 5 coin tosses uses up a lot of space on the tablet. Yep. Well, it assumes that the coin has to land on one of the two sides. It cannot land on an edge and stand on the edge. So that means, every time you toss a coin, the outcome is either a head or a tail. So that means when you add up the probability of landing on the head and landing on the tail, it has to add up to 1. It means P and Q are different. They're not both zero point 0.5. So one is zero point 0.6, the other one is zero point 0.4, one is 0.55, the other one is 0.45. So that means the coin is loaded and it's not even. All right, so I'm switching to the tablet screen just to give you guys a visual of, how we can figure out, all the probabilities of a loaded coin being flipped 3 times, and how do we calculate the chances of, let's just say, 2 heads and 1 tail. Okay, so we start from the beginning. Okay, wrong tool. Here we go. This is the beginning. And we'll use the usual convention, or the one convention that I used before, head tail like this, okay? And then we have head tail like this. And then we have finally, the leaf nodes, okay? Head, tail, head, tail, and finally another head, tail. Okay, so we have seen this already, and this time, as I said, 5 coin tosses is too many. It's more than what we need to illustrate the point, and yet it's going to take us a lot of time. So, but this time the focus is not, a head versus a tail, but also, the probability. So we already know that the chance of landing on the head is P. So everywhere you see a H, there's a P, okay, because P is representing the probability, which is always from 0 to 1, and then tail is going to be Q, okay, because that's the probability of landing on the tail, like so. So we also know that P plus Q has to be exactly 1 because it can either be landing on the head or tail, but there's not a third choice. All right. So now the question is, I'll just pick a random branch or random leaf node. We'll pick this one over here, okay? And it is representing a tail, head, tail, okay? But what is the probability to land on this particular leaf node? Well, let's take a look. In order to get here, the first branch has to take this little arc over here. So that means, we have a Q probability to even land over here. And then once we land over here, we have to take a head. So that has a probability of P. And then eventually, once we are here, then we also have to traverse this branch here or this arc here. So it has another Q. So that means the actual chance of landing on this particular node or leaf node is going to be P times Q squared. So are we getting this? Okay. Are we understanding why it is multiplication? Because to land here, we have a probability of Q. So that means, out of all the probability from this point on, the probability to end up here is P, but then you have to multiply Q and P to basically calculate the chance to end up here. And to take it one more step, to land over here, you also need to multiply Q one more time so that we end up with PQ squared. Yep. We are tossing a coin 3 times, and we want to figure out what is the probability to land on something that has 2 heads and 1 tail. Okay. So now we want to identify all the ones that are actually two heads and one tail. So that is not too difficult. Okay, so this is head, head, tail. This is one of those. Okay, so we want to take a look at this one. The probability to end up here is p squared q. Then we have head, tail, head, which is this one, which is also p squared q. And then we have tail, head, head, which is over here, which is also p squared q. And I think that should be it. Okay. All right. So now we have three of these. So that means um, we have to multiply this by three in order to get the actual probability of landing two heads and one tail out of three coin tosses. Are we doing okay so far with this? Okay. So we also want to double check. Are we supposed to have three um, experiment outcomes that are two heads and one tail? So the way we verify that is to use the equation that we have just learned, or we have introduced on the other day, which is three choose two, three tosses, two of which need to be heads, and then we also want to. So this is 3 factorial divided by 2 factorial times 1 factorial as the denominator. So that's exactly 3. So I just double checked to make sure that I did not miss one of the experiment outcome that is also a 2 head, 1 tail outcome. So are we good so far? Okay. But the probability is no longer, this number, okay, because otherwise we look at this number, okay, sorry about that, 3 choose 2, divided by 2 to the power 3. That would be the probability if the coin is not loaded. In other words, if P and Q are exactly the same, then the probability is exactly that ratio, which is something that we just mentioned in today's lecture. But because the coin is loaded, the probability is not going to be like that anymore. Instead, the probability now is 3 choose 2 times p squared times q. So that's going to be the actual probability for a loaded coin because we have three branches that each one has a probability of p squared q, but we have three of those, so the chances of landing on any one of those three is 3 times p squared q. All right, so is that working out okay? Okay, is the visual helping? Okay, so for people who are visual, I hope the visual is helping. All right, so now we're going to take um, this whole thing and abstract it because um, we want to deal with problems that are a lot bigger than this. Okay, let's just say that we know the probability of a single bit transmitted correctly versus incorrectly, and we are looking at the chances of a packet of 1024 bits having more than 4 bits errors. Okay, do you want to draw that tree? Okay, how big would that tree be? Tell me. How many leaf nodes are we looking at when we are looking at the transmission of a packet that has 1024 bits, which makes it a pretty small packet, okay, by the way, because it's only 128 bytes, okay? But how big is that tree? How many levels do we get? Yep, that's the number of leaf nodes, okay? That's a lot of nodes. So it's best not to rely on a visual graphical approach to solve a problem. It's best to kind of abstract this and go like, okay, in terms of an equation, how do we do this? So that's what we're going to do next, okay, is to turn this into an equation. So essentially what we are really looking at, so let's just say that we have n, coin tosses, okay? So we'll just say that this is n coin tosses, okay? And P is the probability of landing on the head. Q is the probability landing on the tail. And obviously, you can transform a problem into coin, head, and tail, like the packet problem. In the packet problem, n is the number of bits, and every time a bit is received, there's a chance of receiving it correctly, which will just randomly label that as head, and then the other one is going to be receiving the bit incorrectly, which is our tail. So we are basically transforming a problem into something that is a little bit easier to kind of visualize. So that means, so now the question is, if I were to toss this coin, n times, and I want to know, I want to know the probability distribution. Okay, what are the chances that all 1,024 bits are transmitted correctly, which is probably a good thing. And then what if I'm looking at 1,023 of those bits are transmitted correctly and one bit is transmitted incorrectly? So we want to know the distribution. So this becomes a problem of figuring out that, because every time we flip a coin or every time a bit is received, we are looking at, there's a chance that we'll receive the bit correctly, and there's a chance that we might receive the bit incorrectly. So we are looking at something like this, and this really jives with the picture that we drew earlier. Okay, because this is just one of the many outcomes. This is also one of the many outcomes. This is also one of the many outcomes. So now we are really looking at this, and some people would say, but Tech, that's easy because P plus Q has to equal to 1, so this term equals to 1. Yes, I know that too, okay? But what I'm really trying to get to is, we know that out of this multiplication, there's a term that is P to the power of N, there's a term that is Q to the power of N, there's a term of p times p to the power of n minus 1q. There's a term of p to the power of n minus 2q squared, blah, 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 blah. Okay? What I really want to know are the coefficients for each one of these terms. Okay? In other words, if I were to say, okay, this is k0, this is k1, this is k2, blah, 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 and this is kn, I want to know the case. I want to know the coefficients, because the coefficients is what is telling me the actual probability. Is that okay? This really goes back to quadratic equations and stuff like that. So that's algebra. Okay. All right. So we'll go ahead and start with something simple. Okay. We just look at p plus q to the power of 0. What is that? That's just 1. Okay. There's no other way to say this, right? Okay. Q. That's just q, p plus q by itself. Okay. Easy. P plus q squared is, oh, okay, what is this? Yep. And then what about the next one? P cubed plus 3p squared q plus how many pq squared? It's 3 of those plus q cubed, blah, blah, blah. Okay. So if I were to ask you what is p plus q to the power of 4, how would you do it? Are you actually going to use the distributive law of algebra to try to figure this out? Or are you going like, I know about there's a triangle named after a person that has something to do with this. Pascal's triangle. Very good. Okay. So Pascal's triangle. Okay. How many people know what is Pascal's triangle? And why is the rest of the class not raising your hand? It wasn't taught. I am shocked. Okay. So part of me, this is not me trying to criticize people. It's not me trying to, question people's answer, but I really want to know. Okay, I just want to know. Huh? Or Pascal's, what is that? Um, Wager. Yeah, Pascal's wager is also what most people know about. All right, so I'm gonna ask ChatGPT. Is Pascal's triangle supposed to be taught in high school in California? We'll see. Okay, I'm really curious about the answer. Is not explicitly mandated in the California Common Core State Standard for Mathematics. However, its concepts are often integrated into high school curricula, particularly in the Algebra 2 or Pre-Calc, to support the understanding of binomial expressions and guess what? Combinatorics, which is exactly what we are doing here. Okay, very good. For instance, the CPM educational program includes a section on Pascal's triangle and the binomial theorem in this high school curriculum, which is also what we're going to talk about today. So, to some people, this is going to be a rather boring lecture, okay? Because this is more or less a repeat, but I'm focused more on the proof, okay, of Pascal's theorem as no the binomial theorem using Pascal's identity, okay? So even for people who understand what is Pascal's triangle already, this class is about why it works. Okay, so eh, some people, everybody get something out of today's lecture. I hope. Okay, all right. So if Pascal's triangle was not taught, I will just kind of talk about it. Okay, not a problem. So the way it works is you start with one, and then you start with 1 1, and then you have 1 2 1, and then we have 1 3 3 1. Okay, this part of the triangle corresponds to what we worked out a little bit earlier. So for people who do not know what is Pascal's triangle, can you look at this and figure out the pattern of what goes next? Okay, so tell me what goes next. 1 4 6 4 1, and then the next row is going to be mm-hmm. All right, very good. Okay, so if you notice the pattern despite not knowing what is Pascal's triangle, I would say computer science is compatible or aligns with what you instinctively is interested in doing because it's all about noticing patterns. Okay, because what we notice is the outer edge are always ones. Okay, so they are always ones here. And then whatever is not at the edge is the sum of the two numbers on top of it. Okay, so that makes this one a 6, this one is a 15, this one is a 20, this one is a 15 again, and this one is a 6 again. So that is the pattern. Now, for those people who want to say, I don't like the exception of an edge, okay, because that means I have to kind of compare things, whether there's an edge or not. One way to look at this is an island in a sea of zeros. Everybody else are zeros, okay? So that will make it also work because, now when you look at this one here, you know, there's an implicit zero here, right? Because it's an infinite sea of zeros. So there's an implicit zero here. So that makes this always has to be a one. So the only thing that is difficult to explain is the first one. Once you explain the first one, the rest is like, oh, okay, we got it. There's a pattern. All right. So are there any questions about Pascal's triangle, what it looks like? No questions? All right. So these turn out to be the coefficients. Okay. So these are the coefficients of this is corresponding to just one. This is corresponding to p plus q. This is corresponding to p plus 2pq p squared, sorry, p squared plus 2pq plus q squared. This one is corresponding to p cubed plus 3p squared q plus 3pq squared plus q cubed, and so on. In other words, this is how we can figure out all the coefficients when we're looking at p times p plus q, the whole thing to a certain power. Okay, so we are starting with to the power of 0 here, to the power of 1, 2, 3, and so on. Okay, so it's a fairly easy, mechanism to understand, and it's really graphical. So for people who are kind of, who are visual, this is something that's easy to understand. The question is, why does it work? And then some people were asking, why do you always care about why things work? Because, okay, why do you think that is the case? Why do you think tech always question why things work? Oh, I like that question. Yes. So you can relay that, yes, but in the process, and you guys would go like, but Pascal already figured this out hundreds of years ago. Why are we even doing that these days? Yes. Yes, exactly. So when I think Microsoft, the CEO of Microsoft just told people that 30% of the code of Microsoft is written by AI. So I'm just waiting for the day when Microsoft goes like, we need to hire people to fix the code, because I think that day is gonna come, which means, well, it's good news for people who know how to debug programs. Now, how does debugging programs have anything to do with what we are talking about here? Having the mentality of understanding why things are the way they are. Okay, because a bug is a symptom, right? Your program doesn't do what it's supposed to, and instead it's doing something else. That's a bug. So the mentality is, I need to figure out why that is the case. So it's always about the reasoning and the analysis. So this type of analysis is good practice. As much as it doesn't look like programming, doesn't look like debugging, the process to figure this out is actually overlapping with the skill set that you need to debug a program, to figure out why something is not working or why it's working the way it is working. It may not be necessarily wrong, but you need to figure out why it is doing the thing that it's doing. All right, so that's kind of the backdrop of today's lecture, is why does it work? How come Pascal's triangle looks like this and it seems to work? So we go back to the diagram here. So the first thing we're going to talk about is called Pascal's identity. In other words, if I add n choose k and n choose k minus 1, I get n plus 1 choose k. That's Pascal's identity. This equality is called Pascal's identity, and obviously k can only go from 0 to n itself, okay? Um, yeah, not really. Uh, k can only go from 0 to n minus 1. Let me see. Because we know the bottom cannot exceed the top, so it can be 0, but it can be 1. Okay, I take it back. So k can only go from 1 to n. It cannot be negative because the bottom of the combination operator cannot be negative. All right, so now we are trying to understand the algebra behind this whole thing. Okay, now this is just my derivation, which may not be optimal. Okay, I just found a way to arrive to the equality from the top to the bottom, which may or may not be the best or optimal, the most optimal way to do it. So we'll try to figure out line by line, row by row, how this works. Okay. On the first row, how do I make this equality happen? In other words, why do I say n choose k is n factorial divided by k factorial times the factorial of n minus k? Why? This is actually a this is an easy question to answer, because that's how it's defined. Okay, this is how it is defined, which is kind of a good. This is a good time for I addressed your question. So this is a good time for you guys to kind of reflect a little bit and ask, oh, do I remember the definition of n choose k? Because we mentioned it in the same module a while back somewhere. Maybe not this one, but we definitely talk about the choose. Yeah, it's in the previous one. It's in the previous module. So that means if you are not associating n choose k to expand to this format here, you might need to restudy or review all the definitions because this one is by definition. Not knowing something that is by definition means that you need to review things and take notes and make sure that you have it in your own notes. All right, so that also explains the other one because this one is n choose k minus 1. And if you expand, you're using the same template where k is, everything that was k becomes k minus 1, basically. Okay, from the first line to the second line, what do I do over here? I do a little bit of algebraic, manipulation. So here we have n minus in parentheses k minus 1, and then over here we just change the ordering of things a little bit. It becomes n minus k, and then the whole thing plus 1. So is that good so far? Okay, and that's it. That's the only change. And then from here to here, what is the change? From 2 to 3, what is being changed from 2 to 3? Mm, I use the telescoping thing about factorial. Now, telescoping means you can collapse things by just doing some really kind of funky stuff. So imagine that I multiply the numerator and the denominator by k both. Okay, so because if I multiply the numerator and the denominator by a non-zero constant, it doesn't really change the value because k divided by k is 1. But the top doesn't have much magic to it. Multiplying n factorial by k is just n factorial times k. No, not too much going on there. The bottom one, on the other hand, there's some cool stuff that we can do because when you multiply k to k minus 1, the whole thing factorial, you get k factorial. Is that part okay? Let me just isolate that onto the tablet so that you can see it. Okay, so we are talking about k times k minus 1 factorial is just k factorial. Is that understood? Okay, I'm gonna ask a very annoying question. Super annoying. Why not? What does k minus 1 expand to? Okay, k minus 1 factorial expands to k minus 1 times k minus 2 times k minus 3, yada, 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 down to 1, right? Isn't that just k factorial? There we go. That's why. Okay, so this is called the well, this is what I call the telescoping effect of factorial. Okay, um, so it's a really cool and interesting trick to use in algebraic, manipulation when you're dealing with anything that has factorial in it. All right, so that is how we can take out this k minus 1 factorial and turn it into k factorial. The objective is to have the two parts of the sum here to have exactly the same denominator because that way we can combine the numerators. Okay, so that's the objective. That's why we're doing these manipulation. So now we go like, okay, what about from here to here? Okay, from here to here, I divide both the numerator, which is n factorial k, and the denominator of the same fraction. I divide both by n minus k, the whole thing plus 1. So the numerator, there's not much we can do about it. It's just n factorial k, and then divided by n minus k, the whole thing plus 1. But the bottom one is using the telescoping effect again, because if I divide n minus k plus 1, the whole thing factorial, by n minus k plus 1, I'm just taking out the first term of that factorial. So I just have the remaining term of the factorial, which is n minus k, that whole thing factorial. Is that okay? It's the reverse of what I just did. So are we getting that? It's an algebra thing, but it is also specific to factorial. Does anyone want me to kind of talk about this one? Kind of isolated, or you guys are getting it? Getting it? Okay. All right. So now we have this rather messy, numerator, but the denominator looks good, okay? Which is more important to us. So now from 4 to 5, okay, from 4 to 5, the right-hand side of the addition is not changed. The left-hand side is. So what I did to the left-hand side in this case is to multiply n factorial by 1. But that 1 is expressed as n minus k plus 1 divided by n minus k plus 1. Is that okay? So I'm introducing a term on both sides. So we ended up with 5 at this point. Okay, so let's move on from 5 to 6. So from 5 to 6, I'm just combining the two, because now we have a common denominator. So I can just add, I can use a sum of the numerator with a common denominator in this case. So you can also see that just within the numerator, they also have the same denominator of the numerator. So, so the whole thing just becomes this term over here. It's a little bit tedious in terms of, the math involved, but, it's just the way it looks, okay? So are we okay from step 5 to step 6? All right, so from step 6 to step 7, what did I do over here from step 6 to step 7? I moved the denominator of the numerator to the overall denominator. That's all I did. Okay, but then that allows me to go from 7 to 8, which is also using the telescoping effect again, because when you multiply n minus k plus 1 to n minus k factorial, you just get n minus k plus 1, the whole thing factorial. So that's kind of we're almost there, okay? So by go from step 8 to step 9, I just rearrange things a little bit so it looks different. So instead of writing it as n minus k plus 1, I group the plus 1 to n and then the whole thing minus k. So I'm just reordering things and put in parentheses that would otherwise be unnecessary, okay? But I do that for a reason, because when we get to 9, then we can reverse the whole process and go like, oh, but this is really the definition of n plus 1 choose k. Because n plus 1 choose k is n plus 1 factorial divided by k factorial times n plus 1 minus k factorial. All right. The equation, the definition of choose is in the counting module. So if I were to go back to the counting module, and look at combination without replacement right there. So this is where we first encounter the definition of n choose m, or we're trying to figure out the number of ways of choosing m out of n, and that's the definition. But that definition by itself also has an explanation because it's derived from permutation. Because when we count permutation, we are counting duplicates that belong to the same combination, and that's why we have to uh, account for the m factorial, because for every combination of m things, there are m factorial duplicates of in when we count the permutations. So there is a reasoning for everything, and I think it is important to understand all the reasoning, because once you understand the reasoning, the actual formula or the actual definition makes sense. And things that make sense are easier to remember, at least to me. Okay. If I have to remember something, it has to make sense to me first. All right. So I just want to point out where this first appeared and how we derived this in the first place, which is actually important. Um, and then we go back here. Okay, so now we have Pascal's identity. So Pascal's identity is really just saying n choose k plus n choose k minus 1 is n plus 1 choose k. Is that okay? Does everybody understand the actual theorem, okay, or the actual identity? So if I were to zoom out a little bit, this term equals to this term. That is Pascal's identity. All right. What does that have anything to do with Pascal's identity? Well, I mean, the obvious part is they start with Pascal's something, right? Okay, what about the second part? So the second part has to do with, um, let's take a look at the at Pascal's triangle again, and I need to go back to that one. Okay, so we now, oh, okay, wrong thing to do. Go back to the slide here. So this one here is really saying of nothing, I choose nothing. In other words, this one is really asking, um, what is 0, choose 0. Okay, we start everything with 0. And are we convinced that there is one way to choose nothing out of nothing? So this one is conceptual, okay? Because there's no there's I mean, I can give you a visual, but I'm not sure whether it's going to make sense. I give you a bag that is empty. I give you another bag that is empty. And I'm asking you to take nothing out of the first bag to put it into the second bag. And I'm asking you get how many ways can I take nothing out of a bag that has nothing and put it into another bag? One. Exactly. The only outcome is the second bag that I gave you. It will have nothing in it. That's one outcome. Okay? Even though the bag is empty, it is a outcome. So that's why 0 choose 0 has a value of 1. Is that okay? So when we look at this one here, this one is actually representing 1 choose 0. In other words, the first bag that I give you has exactly one item in it. But I'm telling you, choose nothing out of the first bag to put it into the second bag. So how many ways can you return the second bag to me? Exactly one way. It is just empty, right? This one over here, so let me just put in some arrows here. Okay, there we go. What about this one? This one is really 1 choose 1. In other words, I give you a bag that has exactly one marble in it, and I'm asking you to pick to take one marble out of the first bag and put it into the second bag. So at the end of the whole experiment, how many ways can you do this? Exactly one way. Does that make sense? Are we good? All right. So can someone guess what this value of 1 is representing? So there's a pattern here. Hmm? 2 choose 0. That is correct. This is 2 choose 0. This is 2 choose 2. Okay? In other words, I give you a bag of 2 marbles, and then the experiment is take 2 items out of the first bag and put it into the second bag. And ordering is not important. So how many ways can you return the second bag to me? Only one way, because both marbles have to be in the second bag, and there's only one way. Does that make sense? So what about this guy in the middle? What about this 2 here? What is that corresponding to? How many choose what? 2 choose 1. That is correct. Okay. So I give you the same bag with 2 marbles, but this time I'm telling you, um, you know, take one marble out of the first bag and put it into the second bag. So now there are 2 possible outcomes. So let's just say one is red and one is green, right? So the first outcome is you just have the green marble in the second bag, and then the second outcome is you just have the red marble in the second bag. All right. So I'll be starting to see how Pascal's triangle and Pascal's identity are related. because when you look at, well, I'll just pick this one here. So this one is supposed to be what? What choose what? 3 choose 1. That is correct. And it turns out to be this one plus this 2. So that means, oh, that is Pascal's identity. So Pascal's triangle is really just a more visual representation of Pascal's identity. Pascal's identity is the reason behind Pascal's triangle. Are we doing okay so far? Essentially, the rows are controlling the number of items to begin with in the first bag, and then the quote unquote columns. I will draw another picture to show you why I can call those columns. The columns are corresponding to how many things are we removing from the first bag to put into the second bag. So you guys go like, I don't see columns. Well, you just have to tilt your head a little bit. That's one column. This is another column. This is another column, another column, another column, another column. So we have rows, we have columns. The rows are representing n, the columns are representing k. That's it. So the entire leftmost column of ones, that's column 0. That means when k equals to 0. And so you just count the columns, from 0 all the way to the right-hand side and just increment by 1 for each column. And then the rows are the ends. So this really has everything to do with Pascal's identity. So let me switch back to Pascal's identity so you can relate those two. There we go. N is the row, K is the column. So if I know the row of if I already know a previous row, the next row is just going like, oh, okay, just add the two items, quote unquote, on top of me, and that will be my value. Is that okay? Yes. Mm, I'm just going to say that the row number is n, and then the column number is k. So it's not exactly the same thing as array indexing because we don't have a square array. We have a kind of like a triangular thing. Yep. Which one? Pascal's triangle? Because this tells us that because n is or how many we choose from is the row number. So that means if I have the previous row already figured out, then the next row is really just going like, oh, okay, we just add the two numbers on top of the same column together, and that becomes this value. That was actually illustrated in the visual today because you can look at this 3 here. This 3 is representing 3 choose 1, but it is the sum of this one, which is 2 choose 0, plus this 2, which is 2 choose 1. But this itself is Pascal's triangle, or Pascal's identity. Pascal's identity. So I think it helps to kind of do it like this. The second one is, oh, you're correct. K minus 1. There we go. So this is, okay, let me fix it. So in this case, in this particular case, so this particular case is saying, okay, k equals to 1, n equals to 2. Nope, this is not that. Nope, this is not that. This is Pascal's triangle. Yep. It uses the same formula. Hmm. Yeah, this one does not do any modding. Okay. Yep. So it may or may not have any relationship with what you're talking about. But we are just kind of focusing on Pascal's triangle, which is what we see here. All right. So let me just, yeah, go ahead. The G function? No, no, it's not similar to the G function. The G function is about counting in a diagonal way, but we are filling in cells in that case, and the same value cannot appear twice. This one is about how do we calculate a cell using the values of the row that is above it. Well, easier and harder at the same time. They are just solutions to different problems. Yeah, and there's a graphical way to look at it. Yep. All right. And you had a question earlier? The first row is row 0. Yep. So if you are to, okay, I know this looks awfully confusing now. This is row when n equals to 0, and this is the row when n equals to 1, and so on. And then the columns is this is column 0, this is column 0, column 1, column 2, column 3, column 4, column 5, and they control the k value. All right. So are we doing okay so far? So let me just kind of ask a quick question. For people who already knew about Pascal's triangle, does this help you understand why it works? Maybe a little. Okay. All right. I'm just looking at the time. So now that we have Pascal's identity, we are going to move on to something that's even more fun. Okay. So we're going to move on to the binomial theorem. This is the binomial theorem. Okay, the binomial theorem is not just saying, oh, p plus q to the power of n is blah. It says for every n that is a natural number, this equality still holds true. Okay, so it's not just a theorem in terms of uh, it's not something that you can just do it by algebra. Okay, because it's not fixing a particular value of n and just say that, oh, p plus q to the power of 3 is blah blah blah. Okay, it is saying, oh, as long as n is a natural number, this equality holds. So it is a little bit more difficult to prove compared to just an algebra question. So to do this, we are using a special technique called proof by induction. Okay, so we'll talk about proof by induction in this particular context, and then I'll give you some additional examples of how to use proof by induction. So when you prove something by induction, I'm just magnifying again, you have to use what we call a base case. So a base case is essentially fixing n in the quantified expression to a certain value. Now, do you have to use 0? No, you don't have to. If you want to use 2, that's fine too. Okay. However, if you use 2, then you have to do the induction step in both directions, both to the positive side and also to the negative side. When I say negative side, it means 1 and 0. Okay. So it is natural usually if the quantification or if the quantifier has a natural end on one side, we want to use that end. So when you're talking about natural number, there's a natural end of 0. But when you're talking about integers, there's no natural end because it expands infinitely on both sides. So fortunately, we're only dealing with natural numbers here. So using 0 to begin with, seems to make sense. So if n is 0, then p plus q to the power of 0 is going to be 1, right? And I can rewrite that 1 as p to the power of 0 times q to the power of 0. And I can rewrite that as 0 choose 0 times p to the power of 0 times q to the power of 0, which then I can rewrite it as the sigma of I equal to 0 to 0. And then inside the sigma, we have 0 choose I, p to the power of I, q to the power of 0 minus I, because I can only be 0. And that is the format of this original binomial theorem when n equals to 0. Does that make sense? Okay. So the base case typically is super duper easy to do because all you have to do is to do it by substitution and then relatively simple algebra, and then we can establish that p plus q to the power of 0 is this entire sigma term, but this whole thing, this entire equality, meets the requirement of the binomial theorem when n equals to 0. In other words, we have now proven one of an infinite number of cases of the original theorem. But this is a very important starting step because now we have one base case to begin with. So do we have any questions about the proof of the base case when n equals to 0? Okay, as I said, the base case in most proof by induction typically is pretty easy to do. The next step is going to be a little bit trickier to understand or to wrap your mind around. In this particular step, we make an assumption that the theorem holds true for some arbitrary k. In other words, we just say that up to k, okay, we know that the theorem holds true. Okay, don't ask me why, what k is. We just know that there exists a k where we can say, yeah, up to here, the theorem is true. Okay, and now what we need to do is to prove the theorem also holds true for the case of n equals to k plus 1. In other words, you assume that it works all the way up to the case of n equals k, and all we need to do is to prove that with that assumption, we can also prove that the theorem holds true for the case when n equals to k plus 1. Are we good so far? All right. So the assumption in this case is basically saying for some k, okay, p plus q to the power of k equals to the sigma of I equals to 0 to k choose I, p to the power of I, q to the power of k minus 1, which is the same thing as what we see here, except, I replace this n with k. So we are making the assumption that there is such a k existing. Is that okay? So now we ask, then what happens to p plus q to the power of k plus 1? And hopefully we can derive something that looks like this, where k are all replaced by k plus 1. Okay, so that's kind of the general idea. So now the first thing we do is we separate the p plus q to the power of k plus 1, and we just break it up into p plus q by itself outside times p plus q to the power of k. Do we have any objection of the first step? It's like, okay, we just take this plus 1 and put it outside of the whole thing, and the rest, is going to be to the power of k. Okay, cool. The second step is how we utilize the assumption. Because the assumption says, oh, let's assume that for some k, we know this equality holds true. So we go like, hey, p plus q to the power of k matches p plus q to the power of k. So now we go like, oh, by assumption, we can now take this whole thing, the sigma thing, and then put it into here. Is that okay? Now, this is a really important step because we are making use of the induction assumption. Okay, so what is that going to buy us? Well, it buys us something like this. In other words, this p plus q that is on the outside of the sigma, because p and q do not depend on I, so that means I can distribute it into the sigma. So everything in the sigma is just now multiplied by p plus q. Is that okay? That's algebra. Okay, it's distribution of algebra. So now we look at this and go like, oh, okay, but we can distribute again. So we have p to the power of I times p, which is p to the power of I plus 1. And then on this term here, we break it out into another sigma. So now we have q to the power of k minus 1 and then plus 1 so that we can absorb this q on the other side. So this part here from this step to this step here is a little bit trickier, but it really boils down to distribution again. Are we good with that? Okay, it boils down to distribution, and then we are just grouping um, the p power and the q power accordingly. All right, so assuming this step is okay, we're going to move on from here to here. So this is also, I think this step is really totally awesome because it is not obvious. All right, so we look at this step and this step here and ask, what is changed? I see what is changed. Okay, um, this part here. Okay, I have to do it on the computer because we have an online person. So we look at this part here and go like, that's exactly the same as this part here, which is good. However, the sigma only goes from 0 to k minus 1 as opposed to from 0 to k. So that means the very last term when I equals to k is now somewhere else. Is that okay? So that exact term when I equals to k means we have k choose k, p to the power of k itself because the uh, k plus 1 times q to the power of k minus k, which is q to the power of 0. So now we are asking, where did it go? Okay, if we take something out, it has to be somewhere else, otherwise we won't have this equality. As it turns out, that term is over here. Q to the power of 0, p to the power of k plus 1 is all the way over here. And then people will go like, yeah, I can see how the product between the powers of P and Q are the same, but the coefficient is different. This is supposed to be K choose K when I equals to K. This one is K plus 1 choose K plus 1. And I say, yeah, what is the problem? What is K choose K? We just explored that earlier. I give you a bag of K marbles, and I say the experiment is to remove K marbles out of a bag with K marbles and give me back the second bag. How many outcomes do you have? Exactly one. So if you say, I'm not quite understanding the conceptual aspect of taking things out of a bag, that's okay. Go to the definition. What is the definition of K choose K? How do you expand K choose K? All right, so we'll do that. Okay, I'll do it for you. Everything I do something for you is not good for you. I just want to make it clear. All right, so K choose K by definition expands to what? K factorial divided by K factorial times K minus K factorial. And what is that? What about K plus 1 choose K plus 1? That also equals to 1. Which matches the marble in a bag example, right? If I give you a bag with X many marbles and the experiment is to remove all the marbles, put it all into the second bag, you only have one outcome. So, okay, so it makes sense from the equation definition perspective. It also makes sense from the perspective of conceptually, okay, we got a bag and we have to remove all the marbles out of the first bag and put it all into the second bag, which means ordering is not important. Yep, okay, there's only one way to do it. So, with that, now we can say, oh, okay, now we can see how this term is really the same thing as this term over here when I equals to k. Are we good with that? Okay. What about this term over here? We can see the what we are summing. This format here is the same as this format over here. However, this one starts with 0 and this one starts with 1. What happened to the case when I equals to 0? So you go like, okay, let's figure out what it means when I equals to 0. So when I equals to 0 in this particular sigma, we have k choose 0 times p to the power of 0 times q to the power of k plus 1 because your I is 0. Okay, you go like, oh, it's over here. But this one is supposed to be k choose 0. This one is now k plus 1 choose 0. Do we have a problem here? Okay, so if your mind is working and go like, oh, okay, Tak, you talked about this earlier in today's lecture. We are removing nothing out of the first bag to put it into the second bag. And I'm asking you, okay, here's a bag of 16 marbles, okay, and the experiment is like, okay, take nothing out of the first bag to put it into the second bag. How many possible outcomes do we have? One single outcome. You can only give me the second bag back with nothing in it. That's the only outcome. So that means whatever choose 0 is going to be 1. And also, let's just say that, I'm not getting the conceptual part of this. I want it to be, in the definition. Let's work out from this whole thing from the perspective of definitions. K choose 0 is k factorial divided by 0 factorial times k minus 0, the whole thing factorial, which is 1. Because by definition, what is 0 factorial? 0 factorial is 1. Yep. Alrighty. So that works out. Okay, the math works out. And if you're not quite getting the whole thing about the derivation, the algebra in the class, I would recommend you to spend some time, after class to kind of restudy this, with my description of what is happening, because it really is important. Okay, algebra is important in computer science. And the screen is flickering because it disagrees with me. All right, so we go from here, to here, okay? And then what do we do from here to here, from this line to this line over here? Oh, okay, I see. Okay, so um, with this I, the second sigma from I to k, I change it so that it is from 1 to k. So that means everything has to be off by 1. Whatever was I needs to be I minus 1 now because the index itself is increasing by 1. So that means, whatever I is has to be I minus 1 so that I can preserve the same value between this sigma and this sigma. Is that okay? And in between these two, kind of the same deal, except that, okay, yep, okay, so this one is not modified yet. But at this point, we have, this sigma has I going from 1 to k. This sigma is also going from, I is also going from 1 to k. So now I can combine the two sigmas. So that means, I have a new sigma, where I goes from 1 to k. And then we just combine this term, this entire term here, with this entire term over here. So you can see that, the power of p and the power of q are exactly the same. So that means the only thing that is different is going to be the coefficients. So by the reverse of distribution, which is factoring, I can now say, oh, okay, they both have the same common factor of p to the power of I times q to the power of k plus 1 minus I. The only thing that is different is the coefficient. So now the coefficients are now isolated into their own sum, like this. Okay, what does that remind you of? Something that we talked about today, that we just talked about today. We have k choose I minus 1 plus k choose I. What does that remind you of? I mean, we didn't use the same letters, but we have the same format where we're choosing from the same number, but the item that we're choosing from that number is off by 1. It is called Pascal's identity. So now we apply Pascal's identity. So we say, oh, okay, k choose I minus 1 plus k choose I is really the same thing as k plus 1 choose I. Is that okay? So that is how um, Pascal's identity is utilized in the proof of the binomial theorem. Okay, and that's why I have to introduce Pascal's identity first, because now we can establish this. So the last step is really to look at this whole thing and go like, hey, this looks like just an extension of this when I equals to 0. This, on the other hand, looks like this when I equals to k plus 1. So we fold the first and the third term into the sigma using the telescoping effect of sigma, and now we just end up with this. So when we end up with this, okay, the last one here, then we go like, hey, we have just proven that the binomial theorem, which is this one here, is also true when n equals to k plus 1. Because if you plug in k plus 1 to all the occurrences of n here, guess what you get? This thing here. So this whole process is called the induction step. We start with an induction assumption that the theorem holds true when n equals k, and then we use that assumption in order to prove that the theorem is also true when n equals to k plus 1. And when you have the basis done, or the base case done, and you have the induction step done, then you're all done with induction proof by induction. Is that okay? So I can give you a non-visual but more story-like, analogy to proof by induction. Okay. So the story is kind of like you are stranded in the ocean. Okay. And here is a cruise ship, parking next to you, but it's kind of far. You cannot jump onto the cruise ship. Okay. In one single step. The base case is you are standing on an island. In other words, you're not drowning, you're on something right now. Okay. The induction step is going to be a little funky, so we're going to abuse sea turtles. So the induction steps says if you are stepping on something right now, there's always a sea turtle that can help you to take the next step to whatever direction you want to take. Is that okay? In other words, we are counting on the kindness of sea turtles and the buoyancy of sea turtles. So that's the induction step. What is the proof? The proof is I can reach the cruise ship. So let's revisit the analogy. Okay. The theorem is I can get to the cruise ship safely without drowning. The base case is I'm standing on something that is solid. Okay. I'm not drowning at this moment. The induction step is if I'm standing on something, I can always rely on a sea turtle to provide me another step so I can always, take a step closer to wherever I need to go without drowning. And that's it. So are you guys kind of connecting the analogy to proof by induction, which is a way of proving something? So please do not report me to you know uh, yeah, the Society for Humane, Animal Humane Treatment and whatnot, because uh, I'll just say this, okay? Assume the sea turtles did this voluntarily. Okay, I think with that said, we're good. Yes, you can draw sea turtles in your answer to remind yourself, what proof by induction looks like. So I hope the analogy helps a little bit, because that's kind of how proof by induction works, because it is really kind of abstract in some sense. So we got 5 minutes, and I can give you another example of proof by induction. Okay, so let's go ahead and do that because I don't want to waste time, with 5 more minutes. Yeah, it's enough time to do it. So I would define a function like this, okay? F of n is um, if n equals to 0, it returns a 1. If not, it returns 2 times f of n um, minus 1, and n has to be a part of the natural number. Okay, so that's kind of the constraint on n. It has to be a natural number. This is how f of n is defined. And I want you to prove that f of n really is just 2 to the power of n. Okay, so this is the theorem. Okay, this is the theorem that I want to prove, and and n is a natural number. Okay, so the way we prove it is we start with the base case, and once again with natural number, the natural base case is when n equals to 0. So the base case or basis, okay, is when n equals to 0. So when n equals to 0, 2 to the power of 0 is 1, but f of 0 is also 1. Done. Is that okay? What about the induction step? So the induction step starts with the assumption. So the assumption is saying for some k that is a natural number, we already know that f of k is 2 to the power of k for some k that is an element of the natural numbers. Okay, so now we need to look at f of k plus 1. F of k plus 1 is guaranteed, k plus 1 is guaranteed not to be 0, right? So that means we cannot take the then case. We have to take the else case. So this has to be 2 times f of k, which is 2 times, and now we plug in the assumption, the induction assumption. So now we say, oh, but f of k is assumed to be 2 to the power of k. So we just go do this, and now we fold the two terms in the multiplication. QED, done. As I said, 5 minutes is more than enough time. But this obviously is a much simpler case here because the algebra portion is a lot simpler in this case. But it still illustrates that you can establish a base case pretty easily. You just plug in one of the least has to be the least value in the case of natural numbers, and that's a pretty easy one to prove. And then the induction step starts with an assumption that the theorem is true for some natural number k. What k really is, we are not going to say. The What you need to do with that assumption is to prove that f of k plus 1, or when n equals to k plus 1, the theorem still holds true. So you start with f of k plus 1. By definition, it is 2 times f of k. And because of the assumption, we can now say, oh, but by assumption, we know that f of k is 2 to the power of k, and now it is just algebra to finish the proof. Okay, now proof by induction is one of the most useful proofs when you want to verify your algorithm. In other words, if you want to use mathematics to prove that an algorithm is correct, it is one of the most useful one because, okay, I ask this kind of fictitiously. Has anyone heard of uh, recursion? Okay. Um, Do you see a resemblance between proof by induction and recursion? Yeah. Yeah, to quote Keanu Reeves, in multiple roles in multiple movies. Yeah, not really. I cannot imitate his voice, but that's something that he says when he says negative. No, there is a almost one-to-one correspondence between proof by induction and recursion. And that is why it is so useful. Then you guys go like, but that only applies to something that is expressed in a recursive way. What about all the other things that are not recursive, that are iterative? We use loops to do it. Well, then convert it into recursive way first. So we'll talk about that next time on Monday. All right. Well, it is a Wednesday, so have a nice weekend. I'll see you all on Monday. Oh yeah, go ahead. Soon. I'm losing your voice. Can you speak up a little bit? Uh huh. Okay, you have to speak a little louder because I cannot hear you. Let me Yeah, I'm bumping up my volume too. Go ahead. Uh-huh. So the final exam, the scope is going to start with probability and counting, and it will end with whatever topic we end with before the final exam. No, it is not comprehensive in that sense, but in order to be successful in the final exam, you still have to remember all your set notations, and it's implicitly um, comprehensive in the sense that we are still using quantifiers, we're still using set notations, so the notations are still being used. Okay. Yep, you're welcome. All right, cool. All right, so I'll stop the recorder now.